In the second part of the gas chapter, we move into kinetic molecular theory. So this is a theory that scientists have come up to help us to understand what's going on with gases. So remember that laws tell us what happens in nature. It is literally the observations that we make that we could use to predict. And then theories tell us the why. So these are the ones that are human derived and can change if we get new information. So there are 5 main tenets of kinetic molecular theory, or KMT. The first one is that gases are molecules or atoms that are in continuous random motion. And they're going to be like kind of like ping pong balls that are being flinged around in space. And it's also important that we note that they're moving in straight lines. So they're not curving because they don't feel forces from each other. So we'll talk about that in a second. We are also, one of the things that we make is that the volume of the gas molecule is negligible compared to the total volume of the container. So if I have let's just say a container here, my gas particles are so small and so far apart from each other that they basically don't take up any space compared to that total volume. We are also making the educated assumption, that there are no attractive or repulsive forces between the gas molecules, or if there is, it's basically negligible. So what this means is that, and it's a pretty good one, if gas particles, they're very far apart from each other, and so they're not going to feel any kind of forces when they're in the gas phase because they're so far apart. The next part is that energy can be transferred between molecules when they collide, but the total kinetic energy does not change. So basically what this means is there's no loss of energy, especially through heat. That's usually how we lose energy. If you've taken physics, this means that we have completely elastic collisions. So you can kind of think of that as if you're playing like billiards or pool, where one of the balls hits another ball and they keep the same amount of total energy. And then the next thing is that the average kinetic energy is proportional to the absolute temperature, which we have talked about already with respect to ideal gas law, which means that as the temperature goes up, then they're going to move faster. So there's a relationship there. So how fast do they actually move? That is related to the root mean squared velocity. So that's a u with a little subscript RMS, meaning root mean squared. So basically, this is a velocity where they take the velocities of each molecule, they square them, they take an average, and then they square root. So that's where the roots come from the square root, and the mean comes from the average, and the s squared comes from squaring them. And so for any given temperature, we know that the average kinetic energy is going to be the same for every molecule. So that means if I have hydrogen or xenon, they're very different molecules, they're different masses, but they have the same kinetic energy. So that can only be true. So remember that kinetic energy is 1/2 mv squared, where v is the velocity. And so in this case, I'm going to actually use the root mean squared velocity squared. And that is the same for any gas if the temperature is the same. So we can think about, okay, let's say I have hydrogen versus xenon. Who's going to be moving faster? And so, as I asked in class, many of you have guessed that hydrogen would move faster, and that is true because it has a lower mass, so its velocity is able to be higher because the kinetic energy is the same. And if for xenon it has a bigger mass, so it therefore is going to move slower to compensate. And we can see that here on this graph, we know that the speed is greater for smaller molecules with a lower mass than for heavier molecules. So we can see hydrogen here moving in general faster, there's that average, at a higher speed compared to oxygen has a lower speed. The kinetic energy is also, I'm going to write over here, is equal to 3/2 RT. So that's another way that physicists have related kinetic energy to temperature. So what we can do is set these equal to each other, since kinetic energy would be the same. So we'd have 1/2 mu squared equals 3/2 RT. And then what we're going to do is solve for the velocity. So I'm going to multiply, or I'm going to divide by 1/2 and divide by m, divide by 1/2 and m. Oops. And then what I get is that the root mean squared velocity squared equals 3RT over m, and then I square root it to get rid of that squared. And so this is my overall takeaway, is that the root mean squared velocity is equal to 3RT over m. Now in this case, m is molar mass in kilograms per mole. So you're going to take your molar mass of that you find on the periodic table and divide by 1,000. And our R here, since we've been talking about kinetic energy, is the energy R. So that's 8.314 joules per mole Kelvin. It's the same as the other R, but we just converted the liter atmosphere unit into joules. So let's calculate the root mean squared velocity of nitrogen gas at 25 degrees Celsius. So root mean squared velocity is equal to square root of 3RT over m. So I need to find T. Now T is going to be in Kelvin. So we're going to do 25 plus 273, 298 Kelvin. And then my mass for nitrogen, N2, is 28 grams per mole. So I'm going to divide by, there are 1,000 grams per kilogram, so that's 0.028 kilograms per mole. So I could plug that in. 3 times 8.31, and I'm going to do the units for this so you can see. For a joule per mole Kelvin, a joule is a kilogram meter squared per second squared, and then per mole Kelvin. And then I have 298 Kelvin divided by 0.028 kilograms per mole. So you'll notice I have Kelvin cancels, moles cancel, kilograms cancel, and I'm left with meter squared per second squared, but then I'm going to square root it so I get meters per second. After I plug all of that in, I get my speed to be 515 meters per second. So we could do the same thing for helium at 25, so same temperature. Now helium has a mass of 4 grams per mole. So that's going to be equal to 0.004 kilograms per mole. So plugging that in, 3 times 8.314 joules per mole Kelvin times 298 Kelvin divided by 0.004 kilograms per mole. And we get, okay, so before we put in the answer, let's think about it. Compared to nitrogen, what should helium be? So they're at the same temperature, so their masses, or their kinetic energy is the same. Now helium has a smaller mass, so we would approximate that its speed should be faster. So after we calculate it, we get that the speed is 1363 meters per second, which is faster. So that checks out from our logic. Okay, so now gases can do a couple different things. First thing that it can do is it can diffuse, and that means that the gas is able to escape through small holes into either a space that has lower pressure or it is completely evacuated. So you're familiar with that if you had a balloon and you just, especially a helium balloon, we can see here, we have a helium balloon, it's really exciting on your birthday, you're like, cool, I'm gonna keep this for a while, and then give it a day or so, and then the helium balloon has gotten smaller and now is not floating anymore. And that has to do with the fact that helium is a really small molecule and actually small atom, and so it can escape a lot faster than bigger molecules like argon or even carbon dioxide or oxygen through holes in a balloon. So effusion is escape. Diffusion is the spread of a substance. Specifically, in this case, we're going to be talking about gases, but diffusion happens even with solutions, of one substance throughout a space or a second substance. So we can imagine, we've had that experience where somebody sprayed some kind of perfume, or, you have a diffuser at your house where an essential oil is put into the air, and then after a certain time, then the scent has spread out throughout the whole room. So that's where diffusion is, and it even works for, like, if I put food coloring in water and I didn't touch it, over time it would eventually completely mix. We can relate how fast molecules, specifically two gases, will either diffuse or effuse with this ratio. So basically what we do is we take our root mean squared velocities of one molecule or atom and divide it by we're taking the ratio compared to another one. If we do that, the 3RT will cancel out, and we just basically get that the rate of one molecule, of molecule 1, over the rate of molecule 2 is equal to the square root of the mass of molecule 2 over the mass of molecule 1. Now, since we're taking ratios, you don't need to turn those molar masses into kilograms per mole. Just make sure your units are consistent. Okay, so let's calculate the rate of effusion for nitrogen and oxygen. So if I'm going to do rate of nitrogen over the rate of oxygen, then I want to write that down specifically so I know that I'm going to do the mass of oxygen over the mass of nitrogen. So I got to flip-flop the numerator and denominator. So I'm going to do square root of 32 grams per mole divided by 28 grams per mole, and I get 1.07 as my ratio. No units, since it's a ratio, those units cancel out. Okay, I like these ones down here. An unknown gas is a homonuclear diatomic. So homonuclear means same nucleus, meaning same element. And diatomic meaning two atoms. It effuses at a rate that is 0.355 times the rate at which O2 gas effuses. So that means that the rate of my unknown over the rate of oxygen equals 0.355. It's important that we write down those ratios so we know how to do the next part. calculate the molar mass of the unknown and identify it. So I'm going to do mass. So rate of O2 is on bottom, so I'm going to put the mass of O2 on top, and then the mass of my unknown will go on bottom. So that means the square root of 32 grams per mole divided by my mass of my unknown. The whole thing equals 0.355, so I can solve for that. So I'm going to square both sides. So 32 grams per mole over my unknown x equals 0.355 squared. Now I'm going to do cross multiplication where I can switch my numerator and denominator from the opposite side of equal sign, and I can get 32 grams per mole over 0.355 squared equals x. And when I get then x, my mass of my unknown is 254 grams per mole. So since it's homonuclear diatomic, I can divide that by 2 to find the mass, so that's what x2 is, meaning that my element's molar mass is 127 grams per mole, which means my molecule must be iodine, so I2. Okay, now, the ideal gas law holds up when those tenets of KMT are upheld. But in the real world and under certain conditions, the ideal gas law really only works when we have high temperatures and low pressures. When we start to get high pressures, we start to squish our molecules together, and now their volumes start to matter. So under high pressure, the negligible volume assumption doesn't hold up anymore. And then because we can see like right away after we hit about 1 atmosphere, we start to really deviate from the ideal gas, which is that red line. Also, when we have low temperatures, our molecules start to move really slowly to the point where if they collide with each other, they don't just bounce right off. They might actually start to feel a force, and that gets us into our next chapter on liquids. So basically, when we either have high pressure and we squish our molecules together, or we have low temperature, we're getting into a new type of phase. So when we have these non-ideal behaviors such as high pressure, low temperature, we can use the van der Waals equation to help us to correct. So there is a pressure adjustment to help us to deal with the molecules attracting and repelling, and there's a volume adjustment to help us with the molecules taking up some space of their own. So this happens under high pressure, this happens under high temperature, or low temperature. So what the van der Waals equation is just a slight deviation from the ideal gas law, where we have pressure plus moles times this factor A over volume squared times by the volume minus moles times constant B equals nRT. So here's PV equals nRT, but with some adjustments. Now A and B are coefficients that are specific to a gas, so you can look them up on a table. But for the sake of you all, I'm not going to make you use this equation, but I will ask that you know that which conditions does ideal gas law break down and what is the effect of that. In our last problem, we're going to put some concepts together. So I have cyanogen. It's a highly toxic gas. It's 46.2% carbon and 53.8% nitrogen by mass. At 25, so I'm going to write that down. Oops. At 25 Celsius, so 298 Kelvin, and 751 torr, 1.05 grams of cyanogen occupies 0.5 liters. What's the molecular formula? And then predict its molecular structure and its polarity. So we can predict the formula from these percentages. Remember, we can turn these percentages into grams, 46.2 grams of carbon and 53.8 grams of nitrogen. You learned this in your last chem class. We're going to find moles by divided by the molar mass. So this is elemental analysis. So what I get is 3.85 moles of carbon and 3.84 moles of nitrogen. Divide by the smallest to get that ratio. So I get 1 carbon for every 1 nitrogen. So my empirical formula is CN. Okay. So now, what is its molecular structure? So we want to know, well, this is the empirical formula. We can find out its molecular formula. Now, it's a gas, so we can put it into our molecular formula or molar mass calculation. That is where the mass times RT over the volume times pressure. So we know that we have 1.05 grams. This is our gas one, so 0.0821 liter atmosphere per mole Kelvin. And then our temperature, 298 Kelvin. Divided by our volume, it's taking at 0.5 liters. And I do need to get my pressure, 571 torr. Divided by 760 torr per 1 atmosphere. And that equals 0.988 atmospheres. So we'll put that up here. When I plug all of that in, I get my molar mass for this being 52.0 grams per mole. So then I can compare. My empirical formula is 14 plus 12, so 26 grams per mole. So I can take a ratio of that. So the factor between my empirical and molecular formula is 52 divided by 26. So that's my molecular formula mass divided by my empirical formula mass. And that equals 2. So that means my molecular formula is CN times 2, which is C2N2. So one way we can draw this, so this is what cyanogen must look like, is the carbons connected to some nitrogens. So we're going to have 8 plus 10 for my valence electrons, so 18. 2, 4, 6, 8, 10, 12, 14, 16, 18 for my terminal atoms. So our carbons both need 2 more. And we know that carbons like 4 bonds, nitrogen likes 3. Nitrogen only has 1 bond here. So let's actually make both of these lone pairs on each of them bonds. That should work everything out. So 1, 2, 1, 2. Now everybody has an octet. So if we look at this molecule, it's linear. Nitrogen has a larger dipole. So it should be pulling that way and that way evenly. And since it's linear on both sides, this should be a non-polar molecule.